Today's topic is about the common tools used for quality control and the use of control charts. Before I start talking about control charts and tools for quality control, I would like to quickly review a figure that is shown on this slide, along with some terminologies discussed in an earlier webinar named Overview of Quality Assurance. Quality assurance is a system that ensures the quality of our products. One dimension of quality is conformance. Conforming to different food safety standards is part of product quality. Quality assurance puts a lot of emphasis on management and management strategies. In contrast to quality assurance, quality control refers to the operational techniques and activities used to fulfill the requirement for quality. An important part of quality control is process control. At different processing points, quality data can be collected by conducting various tests, such as microbial analysis, chemical testing, and sensory evaluation. This data allows us to conduct statistical analysis, also called statistical process control, to determine if the process and quality is under control. In this lecture, we will focus on quality control. I will start with introducing 7 major quality control tools, followed by discussing some common ways of constructing control charts. In the end, I will talk about how to interpret and use control charts. The first quality control tool is CheckSheet. It is very easy to use and is a direct way to show how often specific problems or defects occur in your processing line. As shown on your right-hand side, you can use a CheckSheet for counting and calculating different product defects. This is an example of a cookie assembly line. The checklist lists 2 major defects: broken cookies and missing fillings. Each day, the number of every defect is recorded. At the end of each week, the total number of defects can be calculated for the entire week for every type of defect. Or, the total defect of every day can be seen as well. The second tool is called the parental chart. It is a bar chart that illustrates percentages of various defects. There are 2 components on this chart. As shown on your right-hand side, the height of the bar represents the frequency of each defect. The orange line on top represents the cumulative percentages. The final total of defects equals to 100%. Taking the figures on this slide as an example, the leaking seal is the number 1 defect, accounting for 50% of the total defects observed. Missing parts and wrong labels are number 2 and number 3. The third quality control tool is called the cause and effect diagram, or fishbone diagram. The idea is to identify all possible reasons that could account for a final product failure. It provides a pictorial representation of the main inputs, causes. A fishbone diagram is typically used when the product failure has been identified and potential causes of the failure need to be identified. For this particular example, all 6 factors, from low-quality ingredients to a poor sanitation program, can contribute to the product failure. A histogram is the 4th quality control tool. It's a diagram showing the frequency distributions of a set of data. This example shows a total of 28 measurements. These measurements were taken for plums that were received at a packing house. Among the 28 randomly selected samples, 9 fell into the range of 40 to 50 millimeter. 11 fell into the range between 52 to 64 millimeter, and 8 fell into the range between 64 to 76 millimeter. If we define the ones above 64 millimeter as large, the ones between 52 to 64 millimeter as medium, and the ones less than 52 millimeter as small, we can have an idea about how many large products we will have for this shipment of plums. The 5th quality control tool is a scatter diagram. It's a way to present data and identify potential correlations between the causes and effects. The example given here shows the correlation between the total bacterial counts of salmon product and storage time. As the storage time increases, the total bacterial counts increase. The regression line indicates quite strong correlations between the two factors. A flowchart is also a quality control tool. It's a direct pictorial representation of the order of processing procedures. Symbols or boxes with words can be used for establishing a flowchart. A flowchart is used as the first step for establishing a food safety plan or HACCP. A flowchart allows us to go over the entire process and identify steps at which control measures can be implemented and verified. A control chart is also a type of quality control tool. As a graph of process characteristics plotted in sequence, a control chart can be built manually by inputting data in programs such as Excel or generated by monitoring systems installed within the processing machine. One example is the Smart Wash system for injecting chlorine into wash water for fresh produce. The monitoring system can check the pH and free chlorine levels in the system in a timely fashion. A typical control chart contains 4 major lines. The UCL is the upper control limit. The LCL is the lower control limit. The center line typically represents the population mean, and the fourth line represents the individual measurements. That's the line going up and down. By plotting all measurements into the figure, we can easily identify the out-of-control point. Based on this figure, we can find the early warning and also times at which corrective actions need to take place. In this figure, the unacceptable limit can be your upper control limit. In some cases, this can also be your lower control limit. When your measurement is above the upper control limit or below your lower control limit, corrective actions are needed. If the control limits are built based on your operational limits, then corrective actions may not be needed, but actions are needed to identify the causes of the out-of-control point. As one can see from this figure, control charts are important monitoring tools to have in order to ensure the quality control programs work. In the second part of this talk, we will go through some examples of control charts. What we have on the screen now is a quality check log from a tomato processing plant. On each production date, samples were taken at different time points to check if the filler was working properly. As you can see, at 6:15 a.m., 3 samples were taken and weighed. They weighed 958, 965, and 955 grams. The total weight, average weight, and the range were calculated. Those numbers are the base for establishing control charts. However, taking subsamples or collecting multiple samples at each time point may not be feasible or needed for certain processing line. The first set of control chart I would like to talk about is named individual and moving range charts. Control charts are typically built and used in pairs, with the first one representing the individual measurements and the second one used for expressing the changes between measurements. For the individual and moving range charts, you can get the idea from the names. While the individual chart is for each measurement, and the moving range chart is for monitoring the changes from one measurement to the next. This set of control charts is used when measurements can be taken continuously and taking subgroups is not feasible or is less beneficial. Using an individual chart and a moving range chart together can provide different information. For example, the top individual chart indicates that one point was out of control. However, when looking at the moving range chart, we can see that 2 values are out of control. The period between the out-of-control point and its previous measurement, and the period between the out-of-control point and its following measurement should both be checked, because both of them potentially could have caused product failure. One typical example for individual and moving range charts is the pH monitoring system in wash tanks. The table shows the measurements taken every 2 minutes continuously in the wash tank, and moving range is calculated between every two numbers. Once those values are calculated, equations listed here are used for calculating the upper control limit, UCL, and lower control limit, LCL. The D4 and the D3 values are constant values that can be identified based on the degree of freedom. For moving range chart, the degree of freedom is 2. For these given examples, both the left individual chart and the right moving range chart show that the process is under control. If we focus on the left individual chart, the blue line is the upper control limit. The gray line is the lower control limit. The right line is the central line. The orange line represents the move of the individual measurement. All of the measurements are between UCL and LCL, indicating that the process is under control. The second set of charts combines an X-bar chart and an R chart. They are used for scenarios where subsamples are taken, like the tomato processing plant example we discussed earlier. The X-bar represents the average of all measurements taken at each time point. R represents the range of the measurements taken at each time point. For example, in this table, at 9:15 a.m., 4 samples were taken and measured. The weights ranged from 15.8 to 16.3. In this case, the X-bar is 16.05 and the R is 0.5. This calculated X-bar and R values are the basis for establishing the charts. Here is one example for an X-bar and R chart. An intensive environmental monitoring program was implemented before the company started production. For this pilot trial, 5 swab samples were taken from 5 sampling spots at each time point. The total Arabic plate counts were obtained by plating. The sampling was done at 10 a.m., 12 p.m., and 3 p.m. each day for 3 days. Taking 10 a.m. on day 1 as an example, the bacterial counts ranged from 5.1 to 5.5 log CFU per swab. The average was 5.24 and the range was 0.4. The two sets of equations shown on top of the slide are used for calculating the upper control limit, UCL, center line, CL, and lower control limit, LCL, for X-bar chart and R chart. X-bar is the average of all measurement. R-bar is the average of all R values calculated at each time point. A2, D4, and D3 values are constant values determined by the degree of freedom. For this example, the degree of freedom is 3, because 4 samples were taken at each sampling point. With the UCL, LCL, CL value calculated, the bottom 2 figures can be built. As we can see from these 2 figures, the X-bar shows 1 out-of-control point. When we look at the R-bar, we don't see any point that go above the UCL or fall below the LCL. When more than 10 measurements are taken at one time point, range is no longer efficient to reflect the changes among measurements. In this case, standard deviation will be used to illustrate the variations. The equation used for calculating standard deviation is listed here, with X-bar representing the average of all measurements taken at each time point. Xi is the individual measurement taken at each time point. N represents the number of measurements taken at each time point. Similar equations, like the ones shown on the previous slide, will be used for building the control charts. with the degree of freedom determined by the number of subsamples taken at each time point. Instead of using a R, S standard deviation will be used. Here's a quick summary of the 3 sets of control charts. When measurements are taken continuously, the set of individual and moving range chart is the best fit. In this scenario, all measurements taken are considered one subgroup. When more than one subgroups are taken, and the sample size is less than 10 for each sampling point, X-bar and range chart are good fit. If more than 10 samples are taken at each sampling point, X-bar and S-chart are better for reflecting the changes and variations. Control charts can also be built based on the numbers or the percentages of conforming and non-conforming products. This type of charts are also named attribute charts. For attribute chart, the non-conforming or conforming products are counted rather than measured. For example, in the table on your right-hand side, the number of Listeria-positive samples were counted each month, and the percentage were calculated. To determine if the cleaning and sanitation programs still work or not, a chart needs to be built based on the numbers of non-conforming products. If we are using the number of non-conforming products to build the chart, then it's named NP chart. When we use the percentage of those non-conforming products to build the chart, it's named P chart. Here's one example. The table on your right-hand side shows the number of drums of Pecos produced every day from October 4th to November 14th. The number of defect products were recorded for every single day. The percentage of defects for every day was also calculated. To build a control chart for this, there are 2 main numbers that need to be calculated. One is the P-bar. It represents the average of all defect product percentages calculated for the entire month. The other one is the N-bar, which represents the average of drums that produced every day. For this particular example, the P-bar is 3.3% and the N-bar is 519. We build the chart. P-bar will be the center line. To calculate the upper control limit and lower control limit, we will follow the equation listed in the blue box. After calculation, we see that the upper control limit is 0.056 and the lower control limit is 0.01. Once we plot all the numbers in this chart, we can see that all the percentages are below the upper control limit and above lower control limit, indicating that the process is under control. Once the control charts are built, the next step is to look at the charts and determine whether there are some potential problems within the processing line. We do expect that variance will happen, as shown in this figure, all values between upper control limit and lower control limit. So this figure indicates that process is under control and is normal. The difference between the previous P chart and NP chart on this slide is that the number of defective or non-conforming products will be used to build the chart. The number of defective products is represented by letter M. If you look at the table on top right, the number of defective products or the M values for each day are listed. In addition, the P values representing the percentage of defective product for each day are also listed. M-bar and P-bar values are critical for building the UCL and LCL values for the chart. M-bar is the average of all M values in the table, while P-bar represents the average of all P values in the table. After the calculation, the UCL value is 23.5, the LCL value is 2.3. Those numbers will be used to build the control chart. If we look at the bottom right, we can see that the number of jars with defects move up and down. All numbers are below the UCL value and above the LCL value, indicating that the process is under control. Once the control charts are built, the next step is to look at the charts and determine whether there are some potential problems within the processing line. We do expect that variance will happen. As shown in this figure, all values are between UCL and LCL, even though they go up and down. This figure indicates that the process is under control and is normal. For this one, we start to see a trend. The measurements are going down in one direction during this period of time. The measurements may also go up in one direction. This situation indicates gradual deterioration of the equipment, continuous change in the environmental conditions, or deterioration of the worker's skill. Whenever a trend is observed, one needs to identify the root cause and prevent it from happening again. If the cause is not identified and the trend happens again, the measurement might drop below the LCL and cause problems to the final products. This figure represents another pattern called abnormal uniformity. The measurements are all at high values with very small variations for a period of time. This abnormal uniformity may be caused by an employee with superior skills or indicate that a key ingredient was not added. The pattern might also be caused by environmental conditions or the wrong control limit was set. Every time a pattern is identified, the root cause needs to be found and corrected. This chart shows a pattern called recurring cycles. These two identical curves might be caused by activities that occur at repeated times. Finding the root cause is again the key to preventing reoccurrence of the pattern. Wild outliers is another scenario. The list of errors include mathematical calculation, plotting mistakes, sampling mistakes, or testing errors. Overreacting to an outlier problem might lead to the next chart, which we call excessive variability. Excessive variability is caused by over-adjustment of the system due to the overreaction to a couple of wild outliers. Identifying the root cause before adjusting the processing line is important to avoid additional problems. In general, you are building control charts to find potential signs of process problems. Typically, if the averages are out of limits, but the variances are not, this indicates serious problems with the process, because all of the observations in the subgroups are already out of control. If the variances are out of limits, but averages are not, the process may be on the verge of developing the problem. If both the averages and the variances are out of limits, something drastic has occurred. It will get worse unless immediate action is taken. Building control charts periodically for the processing system help us identify and verify that our system still works. In summary, there are 7 quality control tools that can be used to monitor and verify the performance of the production system. Control charts are commonly used to investigate if the system is under control. They are built based on the calculation of upper control limit, center line, and lower control limit. Control charts can be built with continuous measurements or samples taken periodically from a processing line. Control charts are important evaluation tools for monitoring the preventive control steps established for your system. They can identify potential problems associated with the system.